We now talk about electric flux. So first step is to consider only flat surfaces. So we have drawn two flat surfaces. So first we have a flat surface which is perpendicular to the electric field. So in the first surface we have the surface S here, where S denotes the surface area and E is the electric field. So this surface is perpendicular to the electric field. So flux in this case is just magnitude of electric field times the surface area. But it could be the case that the surface area is not perpendicular to the electric field. So if the surface area is not perpendicular to electric field, we make it perpendicular. So you construct another surface which is perpendicular to the electric field, and then you can calculate the flux. So let us see this. So say you have this surface which I have drawn in blue, and it is an angle theta with the vertical. So now you can see it is no longer perpendicular to the electric field. But now we can construct another surface area in green from the one in blue. And now this green surface is perpendicular to the electric field. So if original surface is S, the green surface would be S cos theta. So the flux is E times S cos theta. But there could be any surface. Instead of flat, there could be surface of any shape. In that case, we just chop that surfaces into very small pieces. So you take the surface and you chop it into very small pieces and say the small piece is ds. So out of ds you want to make ds vector. Now ds vector is perpendicular to the small surface area ds. So we have a small surface area ds or delta s, and we make a vector out of it. So the question is, how do you make a vector out of this small area ds? So you first take the area and then you multiply it with the normal vector. And normal vector is nothing but a unit normal to the surface which is perpendicular. So unit normal to the surface is always perpendicular to the surface. And this you can read in your mathematics classes. So we are just going to touch on it very briefly here. So basically what we are saying is that if you're given a small surface area ds, you construct a vector ds vector out of it which is perpendicular to the surface. And this is same as constructing a normal to a plane. Now if EI is small flux which passes through this ds. So notice that I have drawn the flux in red in the figure, and this passes through the surface ds, and say theta I is angle between ds vector and this small flux EI vector. So now we are writing dsi and EI just to differentiate that, or to talk about a small patch. So the flux in this very small patch is dot product of EI vector with delta si vector, or EI vector with ds vector. So in terms of integration, when you take the sum over the entire surface area, this becomes integral of E vector dot ds vector. Notice that I have put a circle in the integral. That is because this denotes that we are integrating over an entire surface. So this will be more clear in an example. So we are going to do a simple example, and this is the case 2 of the flat surface. So here in the case 2, you see the small surface area we have to choose first. So you have a small surface area which is, say, ds. Now out of this surface area ds, you make a vector ds vector which is perpendicular to the surface area. Notice that if you take the magnitude of ds vector, it is same as the surface area ds. That is why we are calling it ds vector. So I have, instead of ds, you can also write delta s vector, you're just taking a very small surface area. So now we have to take the dot product of delta S with E vector. So first we need to determine the angle between E vector and delta S vector. So in the figure, on the left hand side, we basically are talking about the plane which is not perpendicular to the electric field. So this is the original figure we had. Angle theta the plane makes with the vertical. Now you have ds vector which is perpendicular right here. And then you have electric field. Now this is ds vector and this side is the electric field. Now the angle between ds vector and electric field will also be theta because these two triangles are similar. So this triangle and this triangle are similar. So now we can apply our formula for flux. So our formula is given as so now we write down our formula for the flux. So we want to calculate the flux through such a surface, and we obviously want to get flux as Es cos theta. So let us write down the formula. So the formula for flux is phi is equal to the surface integral of E vector dot ds vector. Now the flux is not dependent upon the area, but first let us take the dot product. So this will be E ds cos theta. Now E and cos theta are independent of the surface area. You take E and cos theta outside, you get integral of ds. Integral of ds means you sum up over the entire surface, you get S. So the flux you get as Es cos theta.